how supermassive black holes actually form. At the center of our Milky Way galaxy lurks a monster. Sagittarius A star is a supermassive black hole containing 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. And it's not alone. Nearly every large galaxy we observe contains a supermassive black hole at its core, some with masses reaching billions of solar masses. But here's the profound question that has puzzled astrophysicists for decades. How did these monsters form? Black holes from dying stars, we understand. But supermassive black holes are millions to billions of times more massive. Building something that large should take an enormous amount of time. Yet we observe supermassive black holes in the early universe, less than 1 billion years after the Big Bang. They grew impossibly large, impossibly fast. Today, we're diving into one of the most fascinating unsolved problems in astrophysics. We'll explore the leading theories, the evidence supporting and challenging each one, and what recent observations from James Webb and other telescopes are revealing about how these cosmic giants came to be. This isn't a simple story with one answer. It's a scientific mystery still being unraveled. The scale of the problem. Before we explore how supermassive black holes form, we need to understand just how massive they are and why that creates a problem. Let's start with stellar mass black holes, the kind formed when massive stars explode as supernovae. When a star at least 20 to 25 times more massive than our Sun exhausts its nuclear fuel, its core collapses catastrophically. If the core is massive enough, nothing can stop the collapse. It becomes a black hole, typically with a mass between about 5 and 100 solar masses. These stellar mass black holes are well understood. We know how they form, we've observed them directly through gravitational wave detections when they merge, and we've detected dozens of them in binary systems with normal stars. But supermassive black holes are a different beast entirely. The black hole at the center of our Milky Way is 4 million solar masses. The black hole in the galaxy M87, the first black hole ever imaged by the Event Horizon Telescope, is about 6.5 billion solar masses. The most massive known black holes exceed 40 billion solar masses. How do you get from tens of solar masses to millions or billions? The obvious answer would be they grow over time. Black holes can gain mass in 2 ways. First, they can accrete matter from their surroundings, gas, dust, even entire stars that venture too close. Second, they can merge with other black holes, combining their masses. But here's the problem. These processes take time. When a black hole accretes matter, it doesn't just swallow everything nearby instantly. As matter spirals inward, it heats up due to friction and emits intense radiation. This radiation pushes outward against infalling matter, creating a natural limit to how fast a black hole can grow. This limit is called the Eddington limit. For a stellar mass black hole starting at 100 solar masses and growing at the Eddington limit continuously, it would take roughly 700 to 800 million years to reach 1 million solar masses. To reach 1 billion solar masses would take about 1.4 billion years. That seems reasonable, except for one problem. We observe supermassive black holes in quasars when the universe was less than 1 billion years old. Some exist when the universe was only 670 million years old, about 5% of its current age. These black holes are already 1 billion solar masses or more. If they started as stellar mass black holes right after the first stars formed, they would have needed to grow at or near the Eddington limit continuously without interruption from the moment they formed. That's unlikely. Accretion isn't continuous. Black holes go through active phases when they're feeding and quiet phases when they're not. Growing at the maximum rate continuously for hundreds of millions of years is extraordinarily difficult. So we face a dilemma. Either these black holes grew much faster than the Eddington limit predicts, or they started from something much more massive than stellar mass black holes, or both. This is the supermassive black hole formation problem, and it's one of the most active areas of research in modern astrophysics. Theory 1. Stellar remnant seeds. The first and most straightforward theory is that supermassive black holes grow from stellar mass black holes, the seeds left behind by the first generation of stars. In the early universe, the first stars were very different from stars today. They formed from pristine gas containing only hydrogen and helium, no heavier elements. Without heavy elements, the gas couldn't cool as efficiently, which meant that collapsing gas clouds remained hotter and formed more massive stars. These first stars, called population 3 stars, might have been 100, 300, or even 1,000 times more massive than our Sun. They burned incredibly hot and bright, exhausting their fuel in just a few million years before exploding as supernovae. The most massive of these stars would leave behind black holes, potentially with masses of 100 to 300 solar masses, larger than typical stellar mass black holes today, but still far short of supermassive. These stellar mass black hole seeds could then grow through accretion and mergers. Here's how it might work. The black hole sits at the center of a dense star cluster or protogalaxy. Gas from the surrounding environment spirals inward, forming an accretion disk. As the gas spirals inward, gravitational potential energy converts to heat, and the accretion disk glows brightly. The black hole gains mass from this infalling material. Meanwhile, the black hole's gravity pulls in nearby stars. Occasionally, a star ventures close enough to be tidally disrupted, torn apart by tidal forces. The stellar debris forms an accretion disk, and the black hole consumes the star, gaining its mass. The black hole can also merge with other black holes. In the dense environment of the early universe, where protogalaxies were smaller and closer together, black hole mergers might have been frequent. Each merger combines the masses, building up larger and larger black holes. Computer simulations show that this process can work, at least in principle. If conditions are favorable, dense gas environments, frequent mergers, and sustained accretion near the Eddington limit, stellar remnant seeds can grow into supermassive black holes within a billion years. But there are challenges. Feedback is a major issue. As black holes accrete matter and emit radiation, that radiation heats surrounding gas and can drive powerful winds. These winds blow gas away from the black hole, reducing the fuel available for further accretion. This negative feedback can slow or even halt black hole growth. There's also the problem of the earliest quasars. The most distant quasars observed by James Webb and other telescopes show black holes with masses approaching 1 billion solar masses when the universe was only 600 to 700 million years old. Some exist when the universe was only 670 million years old, about 5% of its current age. These black holes are already 1 billion solar masses or more. If they started as stellar mass black holes right after the first stars formed, they would have needed to grow at or near the Eddington limit continuously without interruption from the moment they formed. That's unlikely. Accretion isn't continuous. Black holes go through active phases when they're feeding and quiet phases when they're not. Growing at the maximum rate continuously for hundreds of millions of years is extraordinarily difficult. So we face a dilemma. Either these black holes grew much faster than the Eddington limit predicts, or they started from something much more massive than stellar mass black holes, or both. This is the supermassive black hole formation problem, and it's one of the most active areas of research in modern astrophysics. Theory 1. Stellar remnant seeds. The first and most straightforward theory is that supermassive black holes grow from stellar mass black holes, the seeds left behind by the first generation of stars. In the early universe, the first stars were very different from stars today. They formed from pristine gas containing only hydrogen and helium, no heavier elements. Without heavy elements, the gas couldn't cool as efficiently,
which meant that collapsing gas clouds remained hotter and formed more massive stars. These first stars, called population 3 stars, might have been 100, 300, or even 1,000 times more massive than our Sun. They burned incredibly hot and bright, exhausting their fuel in just a few million years before exploding as supernovae. The most massive of these stars would leave behind black holes, potentially with masses of 100 to 300 solar masses, larger than typical stellar mass black holes today, but still far short of supermassive. These stellar mass black hole seeds could then grow through accretion and mergers. Here's how it might work. The black hole sits at the center of a dense star cluster or protogalaxy. Gas from the surrounding environment spirals inward, forming an accretion disk. As the gas spirals inward, gravitational potential energy converts to heat, and the accretion disk glows brightly. The black hole gains mass from this infalling material.
Meanwhile, the black hole's gravity pulls in nearby stars. Occasionally, a star ventures close enough to be tidally disrupted, torn apart by tidal forces. The stellar debris forms an accretion disk, and the black hole consumes the star, gaining its mass. The black hole can also merge with other black holes. In the dense environment of the early universe, where proto-galaxies were smaller and closer together, black hole mergers might have been frequent. Each merger combines the masses, building up larger and larger black holes. Computer simulations show that this process can work, at least in principle. If conditions are favorable, dense gas environments, frequent mergers, and sustained accretion near the Eddington limit, stellar remnant seeds can grow into supermassive black holes within 1 billion years. But there are challenges. Feedback is a major issue. As black holes accrete matter and emit radiation, that radiation heats surrounding gas and can drive powerful winds. These winds blow gas away from the black hole, reducing the fuel available for further accretion. This negative feedback can slow or even halt black hole growth. There's also the problem of the earliest quasars. The most distant quasars observed by James Webb and other telescopes show black holes with masses approaching 1 billion solar masses when the universe was only 600 to 700 million years old. For stellar remnant seeds to reach this mass in such a short time requires almost perfectly efficient growth, sustained accretion near the Eddington limit with minimal interruptions. This doesn't make the stellar remnant seed scenario impossible, but it does require very specific conditions. The early universe would need environments where black holes could grow extremely efficiently, overcoming feedback and maintaining high accretion rates for hundreds of millions of years. Many astrophysicists think this scenario alone isn't sufficient to explain the most massive early black holes. Something else might be needed. Theory 2. Direct collapse black holes. What if supermassive black holes didn't start from stellar remnants at all? What if they formed directly from massive gas clouds, skipping the star formation phase entirely? This is the direct collapse black hole scenario, and it's one of the most intriguing alternatives. Here's the basic idea. In the early universe, under special conditions, a massive cloud of gas containing tens of thousands to hundreds of thousands of solar masses could collapse directly into a black hole without ever forming a star. Normally, when a gas cloud collapses, it fragments. As the cloud contracts, denser regions form within it. These denser regions contract faster, fragmenting off to form individual stars. This fragmentation process is why gas clouds typically produce star clusters rather than single massive objects.
But fragmentation requires that the gas can cool efficiently. When gas cools, it loses energy and contracts more easily. The cooling happens through radiation. Atoms and molecules emit photons, carrying away energy. In gas with heavy elements like carbon and oxygen, cooling is very efficient. These elements have many electronic transitions that can radiate energy across a wide range of temperatures. But in primordial gas containing only hydrogen and helium, cooling is less efficient. The primary coolant in primordial gas is molecular hydrogen, H2. Two hydrogen atoms bonded together can vibrate and rotate, emitting infrared photons that carry away energy. As long as molecular hydrogen is present, the gas can cool and fragment. But what if molecular hydrogen is destroyed? Ultraviolet radiation from nearby stars can photodissociate molecular hydrogen, breaking it apart into individual atoms. If a gas cloud is bathed in intense ultraviolet radiation, perhaps from a nearby galaxy or star cluster, the molecular hydrogen gets destroyed faster than it can reform. Without molecular hydrogen, the gas can't cool efficiently. It remains hot, temperatures around 8,000 Kelvin or higher. Hot gas has more pressure support, resisting fragmentation. Under these conditions, the gas cloud can collapse as a single entity rather than fragmenting into many pieces. The collapse is rapid and catastrophic. Within roughly 100,000 years, the cloud contracts down to a compact object. At some point during this collapse, the cloud becomes so dense that it's opaque to its own radiation. It can no longer cool by emitting light. The collapse becomes essentially unstoppable, and a black hole forms directly, not from a star, but from the gas cloud itself. The resulting black hole would have a mass of tens of thousands to hundreds of thousands of solar masses, vastly larger than stellar remnant seeds. This head start makes it much easier to reach supermassive scales within the available time. The direct collapse scenario is attractive because it solves the timing problem. Starting from a 100,000 solar mass seed instead of a 100 solar mass seed reduces the required growth by a factor of 1,000. This brings the formation of billion solar mass black holes within a billion years comfortably within reach, even without perfectly efficient accretion. But direct collapse requires very specific conditions. You need a massive gas cloud in an environment with strong ultraviolet radiation to suppress molecular hydrogen cooling. These conditions might have been rare in the early universe, which would explain why not every proto-galaxy formed a supermassive black hole through direct collapse. There's also the question of observational evidence. Do direct collapse black holes actually exist? This is difficult to answer because by the time we observe them, they've already grown and evolved. We can't directly see the formation process that happened billions of years ago. However, astronomers are searching for signatures that might indicate direct collapse origins. One possibility is finding intermediate mass black holes in the nearby universe, black holes with masses between stellar and supermassive scales. These might be descendants of direct collapse seeds that never had the opportunity to grow into full supermassive black holes. Another approach is to look for unusual patterns in how black hole mass correlates with galaxy properties. If direct collapse black holes form through a fundamentally different process than those grown from stellar remnants, they might follow different scaling relationships. Theory 3. Primordial black holes. There's an even more exotic possibility. Primordial black holes formed in the earliest moments after the Big Bang. In the first fraction of a second after the Big Bang, the universe was extremely hot and dense, a roiling sea of energy and particles. Quantum fluctuations created regions that were slightly denser than average. Most of these density fluctuations weren't strong enough to immediately collapse under their own gravity. They expanded along with the rest of the universe and eventually became the seeds for galaxy formation much later. But if a density fluctuation was strong enough, if a region was dense enough to overcome the expansion of space, it could collapse immediately, forming a black hole in the first moments after the Big Bang. These are called primordial black holes. Primordial black holes could, in principle, have any mass. Tiny primordial black holes with masses less than 1 billion tons would have already evaporated through Hawking radiation. But larger primordial black holes would persist to the present day.
If primordial black holes with masses in the range of thousands to millions of solar masses formed in the early universe, they could serve as seeds for supermassive black holes. They'd provide an even bigger head start than direct collapse scenarios, and they'd be present from the very beginning. No need to wait for stars to form first. The primordial black hole scenario is speculative. We have no direct evidence that primordial black holes exist at all, let alone in the mass range needed to seed supermassive black holes. The conditions required for their formation, extremely strong density fluctuations in the early universe, are not generically predicted by our standard models of cosmic inflation. However, primordial black holes remain an active area of theoretical research. They're particularly interesting because they could potentially explain multiple mysteries. In addition to providing seeds for supermassive black holes, they've been proposed as candidates for dark matter, the invisible substance that makes up most of the matter in the universe. If primordial black holes exist and contributed to supermassive black hole formation, we might find evidence in the statistical properties of black hole populations. For example, if some supermassive black holes formed from primordial seeds, or stellar remnants, or direct collapse, we might see a bimodal distribution in black hole masses or other properties. Testing the primordial black hole scenario is challenging, but not impossible. Future gravitational wave observatories might detect mergers involving intermediate mass black holes that could be primordial in origin. Studies of the cosmic microwave background might constrain how many primordial black holes could have formed, and detailed observations of the earliest quasars might reveal signatures pointing towards specific formation channels.
Super-Eddington accretion, breaking the speed limit. Regardless of whether supermassive black holes start from stellar remnants, direct collapse, or primordial seeds, they still need to grow. And one way to grow faster is to exceed the Eddington limit. The Eddington limit arises from the balance between gravity pulling matter inward and radiation pressure pushing matter outward. When a black hole accretes matter rapidly, the infalling material heats up and emits intense radiation. If the radiation pressure becomes strong enough, it can halt further accretion. But the Eddington limit isn't an absolute physical barrier. It's a steady-state equilibrium. Under certain conditions, black holes can exceed this limit and grow faster. One way this can happen is through thick accretion flows. In typical thin accretion disks, radiation escapes easily, creating strong radiation pressure. But if the accretion rate is extremely high, the disk can become optically thick, opaque to its own radiation. Photons get trapped in the infalling material and are advected inward rather than escaping. Without escaping radiation to create outward pressure, the black hole can accrete faster. Another possibility involves the geometry of accretion. If gas falls in along specific directions, perhaps funneled by magnetic fields or arriving preferentially from one side, radiation might escape along other directions without impeding the infalling material. This anisotropic accretion could allow super-Eddington growth rates. There's observational evidence that super-Eddington accretion occurs, at least occasionally. Some active galactic nuclei show signs of extremely high accretion rates. Ultraluminous X-ray sources, compact objects emitting far more X-rays than stellar mass black holes should, might be intermediate mass black holes undergoing super-Eddington accretion, or possibly neutron stars accreting at extreme rates. If early supermassive black holes grew through super-Eddington accretion, even for brief periods, it would significantly shorten the time needed to reach billion solar mass scales. Combined with favorable starting conditions, larger seed masses from direct collapse or primordial black holes, super-Eddington accretion could solve the timing problem. However, super-Eddington accretion has its own challenges. The same thick disks that allow rapid growth also obscure the black hole, making it difficult to observe. And sustaining super-Eddington rates requires a continuous supply of gas, which isn't always available. Black hole mergers, building mass through collisions.
Another way supermassive black holes grow is by merging with each other. In the early universe, galaxies were smaller and closer together. Galaxy mergers were common. When two galaxies merge, their central black holes eventually spiral together and merge as well, combining their masses. Each merger can add significant mass quickly. If a million solar mass black hole merges with another million solar mass black hole, you instantly have a 2 million solar mass black hole. A series of mergers can build up mass faster than accretion alone. The merger process has several stages. Initially, the two black holes are at the centers of their respective galaxies, separated by thousands of light years. As the galaxies merge, dynamical friction, gravitational interactions with stars and gas, causes the black holes to sink toward the center of the merged galaxy. Once the black holes are within a few light years of each other, they form a binary system. The binary hardens through gravitational interactions with passing stars. Stars that wander close to the binary get flung out at high velocities, carrying away energy and causing the binary to shrink. Eventually, the black holes get close enough that gravitational wave emission becomes significant. Gravitational waves carry away energy and angular momentum, causing the orbit to decay rapidly. The black holes spiral together in a matter of years or even days, finally merging in a cataclysmic collision that releases more energy and gravitational waves than all the stars in the observable universe emit in light during the same time. We've detected dozens of black hole mergers through gravitational wave observations. Most involve stellar mass black holes, tens of solar masses. But in the future, space-based gravitational wave observatories like LISA will detect mergers involving intermediate mass and supermassive black holes, revealing how these mergers contributed to black hole growth across cosmic history. Computer simulations suggest hierarchical merging. Repeated cycles of galaxies merging and their black holes combining can build up supermassive black holes efficiently. In models of cosmic structure formation, dark matter halos merge and grow hierarchically. Galaxies within these halos merge as well, and their black holes follow suit. However, there's a potential bottleneck called the final parsec problem. Once a black hole binary reaches a separation of about 1 parsec, 3.26 light-years, stellar interactions become less efficient at removing energy. The binary can stall at this separation unless some other mechanism takes over. Possible solutions include dense stellar environments providing sufficient stellar interactions, gas dynamics funneling material into the center and extracting energy, or gravitational wave emission becoming significant earlier than expected if the black holes have high spins. Despite this potential bottleneck, many astrophysicists believe mergers play a crucial role in supermassive black hole growth, particularly in the later stages when black holes are already fairly massive and accretion rates decline. What James Webb is revealing. Recent observations from James Webb Space Telescope are providing new clues about supermassive black hole formation. James Webb has discovered numerous active supermassive black holes in the early universe, quasars and active galactic nuclei shining when the universe was less than 1 billion years old. Some of these black holes are surprisingly massive, reinforcing the formation problem. But James Webb is also revealing details we couldn't see before. By obtaining detailed spectra of these early quasars, astronomers can measure their masses more accurately, determine their accretion rates, and study the properties of their host galaxies. One intriguing finding is that some early black holes appear to be accreting at very high rates, possibly at or above the Eddington limit. This supports the idea that super-Eddington accretion might be common in the early universe. James Webb has also found early galaxies with surprisingly massive black holes relative to their stellar masses. In the nearby universe, there's a tight correlation between black hole mass and the mass of the galaxy's central bulge, but some early galaxies show black holes that are disproportionately larger compared to their stellar masses. This suggests that in the early universe, black holes might have grown faster than their host galaxies, or that black holes formed before the galaxies fully assembled.
Both scenarios have implications for how we understand the coevolution of black holes and galaxies. Another interesting observation involves the abundance of active black holes in the early universe. James Webb is finding them in greater numbers than previous surveys, suggesting that black hole formation and growth might have been more common in the early universe than models predicted. These observations are helping astronomers test formation scenarios. If direct collapse black holes were common, we might expect to see a population of intermediate black holes or early supermassive black holes with specific signatures. If stellar remnant seeds dominated, we'd expect different patterns in the mass distribution and host galaxy properties. The data is still accumulating and interpretations are ongoing, but James Webb is providing the observational constraints needed to distinguish between theoretical models and understand which formation pathways were most important in the real universe.
The role of environment. One aspect that's becoming increasingly clear is that environment matters for supermassive black hole formation. Not all regions of the early universe were equally conducive to forming supermassive black holes. Dense regions where gas was abundant and galaxy mergers frequent might have produced supermassive black holes more easily than isolated low-density regions. The first supermassive black holes likely formed in the densest peaks of the cosmic web, regions where dark matter and gas were most concentrated. These environments would have provided both the large seed masses through direct collapse or early stellar populations and the abundant fuel needed for rapid growth. Radiation environment also matters. For direct collapse black holes to form, you need ultraviolet radiation to suppress molecular hydrogen cooling, but not so much radiation that it heats the gas and prevents collapse entirely. This requires a delicate balance that might only occur in specific environments. Magnetic fields might also play a role. Strong magnetic fields can transport angular momentum in accretion disks, allowing material to spiral inward more efficiently. In magnetized environments of the early universe, this could enhance black hole growth rates. The metallicity, the abundance of heavy elements, affects both star formation and black hole growth. In low metallicity environments, stars and their remnant black holes might be more massive. Low metallicity also affects how efficiently gas can cool and accrete onto black holes. Understanding environmental effects is crucial because it helps explain why some galaxies have very massive black holes while others have smaller ones, and why supermassive black holes appear at certain times and places in cosmic history. Multiple pathways, no single answer. As we synthesize everything we've discussed, a picture emerges. There probably isn't one single way that supermassive black holes form. Instead, multiple pathways likely operated, with different mechanisms dominating in different environments and at different times. In some regions, population 3 stars formed massive stellar remnant seeds that grew through sustained accretion and mergers. In other regions, special conditions allowed direct collapse black holes to form, providing larger starting masses. Perhaps primordial black holes contributed in some cases, though this remains speculative. Different black holes might have grown at different rates. Some underwent super-Eddington accretion during gas-rich epochs. Others grew primarily through mergers as their host galaxies collided with neighbors. Most probably experienced a combination, periods of rapid accretion punctuated by mergers and quiet phases. This diversity means that studying supermassive black hole formation isn't about finding the one true answer. It's about understanding the relative importance of different mechanisms, the conditions under which each operates, and how they combine to produce the population of supermassive black holes we observe. Modern simulations are beginning to incorporate multiple formation channels simultaneously. Rather than testing one scenario at a time, these simulations include stellar remnants, direct collapse, accretion at varying rates, mergers, and feedback processes, allowing the virtual universe to choose which mechanisms dominate under different conditions. Early results suggest a mix of formation pathways best reproduces observations.
Stellar remnant seeds might be most common, but produce smaller black holes. Direct collapse might be rarer, but produce the largest black holes. Mergers amplify mass across the board. Super Eddington accretion provides growth spurts during gas-rich epochs. Outstanding questions. Despite tremendous progress, major questions remain. We still don't know the typical mass of the first black hole seeds. Did most supermassive black holes start from stellar remnants of tens to hundreds of solar masses, or were direct collapse seeds of tens of thousands to hundreds of thousands of solar masses common? We don't fully understand how super Eddington accretion works or how frequently it occurs. Can black holes sustain super Eddington growth for millions of years, or only in brief episodes? The final parsec problem in black hole mergers remains unresolved. How do black hole binaries overcome the stalling at 1 parsec separations and merge efficiently? We don't know if primordial black holes exist, and if they do, whether they contributed meaningfully to supermassive black hole formation. The relationship between black holes and their host galaxies, the so-called black hole-galaxy coevolution, is still being unraveled. Do black holes drive galaxy evolution through feedback, or do galaxies regulate black hole growth by controlling gas supply? Or both? And perhaps most fundamentally, can we find direct observational evidence distinguishing between formation pathways? Can we observe a direct collapse black hole in the act of forming, or identify remnant signatures in present-day black holes pointing to their formation mechanism? These questions drive ongoing research. Future telescopes with even greater sensitivity, next-generation gravitational observatories, and sophisticated computer simulations will continue to refine our understanding. Closing. So, how do supermassive black holes actually form? The honest answer is, we're not entirely sure, but we're closing in on the solution. They probably start from seeds, stellar remnants from the first stars, direct collapse of massive gas clouds, or possibly primordial black holes from the early universe. They grow through accretion, sometimes at or above the Eddington limit, fueled by gas in their environments. They merge with other black holes when galaxies collide, building mass through cosmic collisions. Different mechanisms dominate under different conditions, and most supermassive black holes likely grew through a combination of pathways. What makes this exciting is that we're living through the era when these questions are being answered. James Webb is observing the earliest black holes, revealing their properties in unprecedented detail. Gravitational wave observatories are detecting black hole mergers, showing us growth through collisions in real time, and supercomputer simulations are testing formation scenarios against observations. Piece by piece, observation by observation, the mystery of how supermassive black holes form is being solved. And with each discovery, we gain deeper insight into the nature of the universe, the physics of gravity at its most extreme, and the cosmic history that led to the universe we see today. The monsters at the centers of galaxies aren't just curiosities, they're key players in cosmic evolution, shaping galaxies, regulating star formation, and leaving their mark across the universe. Understanding how they formed is understanding a crucial chapter in the story of everything. Thanks for joining me on this deep dive into one of astrophysics' greatest mysteries. If you found this exploration valuable, subscribe for more in-depth looks at the science shaping our understanding of the cosmos. And leave a comment. Which formation pathway do you think was most important? Keep questioning, keep exploring, and keep looking to the stars.